Okay, I think we'll get started with this next section, which is the last section that I'll be guiding you through before I hand you over to Ray. So in this part, we'll be looking at indexing, slicing, and subsetting data frames in Python. So in the first part of the lesson, we read a CSV file into a Pandas data frame, and we looked at how we can save that data frame to a named variable, we can perform basic math on the data, we can calculate summary statistics, and we created some plots based on the data that we loaded into Pandas. In this next bit, we'll look at ways to access different parts of the data using indexing, slicing, and subsetting. So I've opened a new notebook. You can just continue in the same one. It was just visually so I could start fresh. I've still got everything here, so if you want to see anything from the last time, I've still got it up, and you can just let me know. So I'm just going to reopen and read the data in again, the same data as we had in the first section. Okay, so we're going to look at indexing and slicing in Python. So, oh no. Oh, I've also not opened it in the right bit. Okay, bear with me. Or maybe I'll just go back to the old one. We'll just continue in this one. It's fine. Yeah, okay. Well, it's not complaining in this window, so we'll just continue in here with that distracting plot above it. Okay, so we often want to work with subsets of the data frame object rather than the entire data frame with all of the data in it. And there are different ways to accomplish this, including using labels, such as the column headings, numeric ranges, or specific XY index locations. So if we want to select data using labels or column headings, we use square brackets to select a subset of any Python object. So we saw that when we were looking at the lists and we wanted to print out the first element, we used square brackets with a 0 in them after the list. And so that holds even when it's a more complicated object like a data frame. So we can select all data from a column named species ID from the data frame by name. So we can do it like this. And that shows us all of the species ID, or we can create, or we can do it with the dot using the attribute methods. So we would type the name of the object, which is the surveys data frame, and then we would type the name of the part of it that we want, so the species ID, and that gives us the same result out. So you can choose which one, they do the same thing. We can also create a new object that contains only the data within the species ID column using the following command. So we'll call it surveys species, and that'll be equal to the name of the data frame, and we only want the species ID column. So we made that variable. We can pass a list of column names too as the index to select the columns in that particular order. So that's useful if we want to reorganize the data. So if we want to select the species and the plot columns from the data frame, you would do it by having 2 square brackets and then typing the column headings that you would like to select, like so. So that gives us this species ID, plot ID, and then we'll look at what happens if I change the order around. So if we ask for the plot ID first and then the species ID, then you can see that it's given us the same data, but just in the other order. And if we ask for a column that doesn't exist, like if you were to accidentally typo and ask it for species, then it's going to throw a big ugly error. But if you look at the traceback for the error, then it tells you that we've got a key error, species, and that indicates that the problem is that this doesn't exist. So then you'd look at it and you'd be like, oh, I've typed that wrong, and that's why I can't have that data. So it's not a column, it's not a valid column name or a valid, if this was a dictionary, then it would also throw a key error because that wouldn't be a valid key. So just as a reminder, the Python language and its modules, like Pandas, define reserved words that we can't use as identifiers when we're assigning objects or assigning variable names. So examples of reserved words in Python include the Boolean values true and false, the operators and, or, and not, among others. There's a full list of reserved words that you can see online if you need to check. So when naming objects and variables, it's also important to avoid using the names of the built-in structures and methods. So for example, a list is already a built-in data type. It is possible to use the word list as an identifier for a new object. So you could say like list equals and then list of things. But if you do that, you can't then do any of the things that you could do with the built-in type list. So you couldn't, there are tricks like list and then empty parentheses would just make you a new empty list normally, but if you've now defined it as something, that won't work anymore. So now we'll look at extracting range-based subsets using slicing. So if we remind ourselves, Python uses zero-based indexing. So the first element is located at position 0, which is different from R and MATLAB. So if I create a list of numbers here, then you can index it via, you can index it starting from 0. So we've got a short exercise on extracting data. I might zoom in on this one so you can see it better. There we go. So if we just give 5 minutes to do this, and I'll scroll so you can see my list there. So if you guys create this list and then try these examples, and we'll come back to it in a few minutes. Okay, so hopefully that was long enough for you all to manage it, because I think this is simpler than the plots that we were making before lunch, but we're just easing back in this afternoon. So if we call A0, that's going to give us back 1 because this is the first element in the list A that we've made. If we try and call the 5th element, which is actually the 6th element, then we're going to get an index error because you can see that, because there's 0, 1, 2, 3, 4. And if you ask for a len A, then the length of A is 5. So if you write A and then try and index with 5 again, it's the equivalent of what we did here. So if you actually want the last element of the list, then you can use the -1 index, which is a pretty useful trick to have. I'll just type those in so that everyone can see. Yep, that returns 1. If we try and do 5, we get an error. If I try and do the length of A, we get an error. But if I do -1, then we get the last element, which was 5. Great. So now we can look at slicing subsets of rows in Python. So slicing using the square brackets operator selects a set of rows and or columns from a data frame. To slice out a set of rows, you use the following syntax. You have the name of the data, and then you open the square brackets, and then you have the start value, a colon, and then the stop value. So like this is our object, and then if we want to take the first 3 rows, we would start at 0, and we would go to 3. When slicing in Pandas, the start bound is included in the output, and the stop bound is one step beyond the row you want to select. So if we want rows 0, 1, and 2, we start at 0, but then the second number has to be one more than the one that you wanted to stop at. So that shows us the first 3 rows. The stop bound in Python, that might be a little different from what you're used to in other languages. It's always good to make sure the different intricacies. So if we want to get another way, if you want to start at 0, you don't always have to explicitly type the 0. So you can just start with the colon, and then if we put a 5, because we want to look at the first 5 rows, then that also works. And if you want to select the last element in the list, we can also do it this way, where so that's selecting the last element, and then if you do the colon and then close the square bracket, that's saying we want to end at the end of the list. And so that will just show us the final row. We can also reassign values within subsets of the data frame. Before we do that, we're going to look at the difference between copying objects and referencing objects in Python. So we'll start with an example. We're going to do a copy first. So we'll give it a very explicit name so we remember which is what here. So the true copy surveys is equal to the surveys data frame. And then we can do this .copy method. And we can also have the reference one. So the reference to the surveys is just equal to the data frame. So you might think that this line 75, ref surveys df, is making a fresh copy of this object because you've set it equal to that. However, if we use the equals operator in this simple statement y equals x, it doesn't actually create a copy of the data frame. Instead, it creates a new variable, in this case ref surveys df, that references the same object that surveys df references. So to state this in another way, there's only one object, which is the data frame, and both of these names will refer to that object. But in contrast, this copy method makes a true copy of it. And to look at the differences between these two things, we're going to look at what happens if we reassign the values within a subset of the data frame that references another data frame object. So for example, I'm going to assign the value 0 to the first 3 rows of data in the referenced one, using the slicing method that we just looked at, and set that equal to 0. And then we're going to try out this following bit of code. So we'll have a look at the head of it. So then we can see all zeros in the first 3 rows. And then if we look at the copy version, it's still got the original data because this is its own separate copy of this. And then if we want to look at the original one, you can see that this is also all zeros because both the ref surveys df and surveys df are amending the same object, whereas the true copy is separate because it was stored separately. Yes, Rui's made a good point about the copying, being careful about copying applies to most mutable objects. So anything that you can change, as we spoke about earlier, lists being mutable, you need to be careful when you're copying and when you're just referencing to the same piece of memory versus the immutable things. Like the tuples that we spoke about earlier. And I'm also not sure about whether sets are mutable now. So yes, the difference between these 3 data frames is that when we assign the first 3 rows the value of 0 using line 76 here, the ref surveys df, it also modified the surveys df because they're looking at the same thing. the exact same object. So if either one changes the object, the other will see the same changes to the reference object. But true surveys was created via the copy function, so that just retains the original values unless you wrote true copy surveys df and made a slice and set all of them equal to 0. So to review that, copy uses the data frame's copy method, and a reference is created using the equals sign and operator. Okay, so now we're going to make a new clean data frame now that I've gone in and meddled and made things different values. And if you've also been following along and typing these things, you'll also want to make a new clean version, and we'll read that CSV back in again. Okay, so now we're going to look at slicing subsets of rows and columns in Python. We can select specific ranges of our data in both the row and column directions using either label or integer-based indexing. So iloc, spelled I-L-O-C, is primarily an integer-based indexing counting from 0. So you specify rows and columns giving a number. So the first row is row 0, the second column is column 1, etc. Whereas loc, so the same but without I at the start, that's primarily a label-based indexing, so you can refer to rows and columns by their name, so the column month or species ID and plot ID like we've been using earlier. So integers can be used, but they're interpreted as a label. So if you were to use an integer, then they would appear in like these labels at the tops of the columns or the rows. So to select a subset of rows and columns from the data frame, we can use the iloc method. So we could select the month, day, year, which are columns 2, 3, and 4, if we start counting at 1, as seen there, using this. So iloc is just a method that you can call. So that then gives us the first 3 rows and the month, day, year columns printed out in a neat little format. So we asked for this first bit of the 0 to 3, we've asked for a slice from 0 to 3, so it's just giving us the 3 rows of data. So let's look at some other ways to index and select subsets of data. So if we want to select all the columns for rows of index values 0 and 10, we can do it like so. There you go, that's all of the ones that have the locations 0 and 10 specified, and then we wanted all of the columns, so they're all printed out there. Cool, and then we'll have a look at this one. So this gives us in row 0, the values from the columns of species ID, plot ID, and weight, which we can verify up here is true. We've got NL, we've got 2, and we've got NaN. And also note that by changing, it will show you them in the order that you've requested them, not necessarily the order that they appeared in the original data frame. And then there's one more to have a look at. Okay, so that's giving me an error because I've asked for index 35549, which is actually longer than the size of the table. But if we type, so although we know that it's got 35549 rows, we have to index it using this, and that then shows us the first, the 10th, and the last row in the table. So you can still, you're always going to get these key errors. But thankfully for these kind of things, the Python error is quite explicit in what it is that you've done wrong. So indexing by labels using the location differs from indexing by integers, which is the iloc method. With loc, both the start bound and the stop bound are inclusive. So when you use loc, integers can be used, but the integers refer to the index label and not the position. So using loc and selecting 1 to 4 will give you a different result than using iloc and selecting 1 to 4. We can also select a specific data value using a row and column location within the data frame and iloc indexing. So we can do using the integer 1 to 6. That gives us F for female. So the index location 2, 6 selects the element that's 3 rows down and 7 columns over in the data frame. So if I print out the start of it again, if we look 3 rows down and 7 columns over, we do get to the F. So you can get individual entries as well as printing out other shaped slices. It is worth noting that rows are selected when using loc with a single list of labels or iloc with a single list of integers. However, unlike loc or iloc, indexing a data frame directly with labels will select columns, while ranges of integers will select rows. Direct indexing of rows is redundant using iloc and will raise a key error if a single integer or list is used, and that error will also occur if the labels are used without loc. A useful rule of thumb is the following. Integer-based slicing is best done with iloc and will avoid errors and is generally consistent with indexing in NumPy arrays if you're used to that. And label-based slicing of rows is done with loc and slicing of columns by directly indexing column names. I know that's a lot of rows and columns in indexing, so there's a little example for you guys to try that'll hopefully help you get your head around it. Is that big enough to see? Let me know if you want it any bigger. Yeah, so if you guys want to try these out, and we'll go through the answers in 5 minutes or so. Just quickly before we go through the answers, we just want to check that the chat is working. So if somebody or a couple of people wouldn't mind posting a test message in the chat. Okay, perfect. Good, we can see that. Thank you. It was just, yeah, we could only see Rui's messages and we were concerned somebody might be needing help and they weren't getting through, but I'm glad to see that it's working. Okay, so we'll go through the answers to this one. So if you type surveys df03, that gives us back the first 3 rows of the data frame. If you try and index just with the 0, that results in a key error because the direct indexing of a row is redundant. If you slice, you can do that to get the first row, and the :5 will give you the first to the 5th rows. And this one will give you everything apart from the final row. So you can use negative index numbers to count backwards from the last entry. You can use you can go higher than -1. So this is it with -1, and the bottom number here is 35547, and then we can do, if I can type it properly, -100, for example, then it gives us even less. Yeah, 35547 and then 35448. So we've gone back 100. I should have picked a different number that would have made it more obvious without having to scroll up and down, but here we go. Okay. And then if you use the iloc ones, then we'll get the first row back. That'll get the first row as a named list. This will give you all of the columns in the first 4 rows. This one will give you the specific columns in the first 4 rows. And then this will give you a type error, because while iloc uses integers as indices and slices accordingly, using lock, because see, this one is lock as opposed to iLock. Lock needs labels, and there are no column names 1 to 4. There are columns 1 to 4, but there are no columns that have the actual labeled name 1 to 4. So then this call is going to result in an error. Nice. Hopefully that's made you a little more familiar with how to move around the rows and columns of the Pandas data frame. So now we'll look at subsetting data using criteria. We can select a subset of the data using a criteria that we've specified. So we could select all the rows that have a year value of 2002 using this command. So there's 2,229 rows that correspond to having a year of 2002, and you can see here, if you look at the year column of the data frame, they've all got 2002. Or we could also select all the rows that don't have 2002. So we use the not equal to. And now we can see that none of these years are 2002. We can also define like multiple sets of criteria. So we can look for all the ones that are greater than or equal to 1980 and less than or equal to 1985. So we're looking for all the entries that have occurred from 1980 and 1985 inclusive. Oh, apart from I've mistyped the parentheses. So we'll try again. Oh, I forgot the year, sorry. See, it's so easy to type the wrong thing. Okay, third time lucky. Important to remember that you have the right column. So the reason this didn't work is because it was trying to compare, it was trying to check whether something was less than or equal to between a string and an integer, which is obviously not particularly possible. So I sorted it by adding the actual column that I wanted it to look at, which only contains integers, so there wasn't a problem. And now we have all of the records that took place between 1980 and 1985 inclusively. So there's a little cheat sheet on the website if you're following along. So you can check if something is equal to something else by using the double equals. Not equals is the exclamation equals, as we saw before. There's greater than, there's less than, and then you can combine them with greater than or equal to, and of course less than or equal to. So you can use all of them to find the parts of your data that you need. So we've got challenges on queries now. So if you guys use these commands to look for subsets of rows, and I'll give you 5 to 10 minutes for this one because there's some experimenting required, but yeah, post in the chat if you need any help with this one. All right, we'll have a look at the answers for this one. So to select the subset of rows that contain data from the year 1999 and contain weight values less than or equal to 8. So you should have got something like this using the AND operator. But if you only want to know how many rows meet the criteria, you could also just find the sum of the true values. So you would do that by having sum before your selection criteria. And that would tell you that there are 5. So hopefully everybody got 5. I will give it a try just to verify after our after the catch that we had earlier. Is that the way? Okay, also 5. So hopefully you all got 5. The second part was about using the isin command to query a data frame based on a list of values as follows. So you can use the isin function to find all the plots that contain particular species. So if you were to look for all of the ones that contain the species codes PB and PL and the plot and get the plot IDs of them, there. So they're 24 if you use these codes. And for 3, they wanted you to find a query that finds all the rows with a weight value greater than or equal to 0, which you could do with this one. That's quite similar to the ones that we did before. And then the last one was how you can use the tilde symbol to return the opposite of the selection that you specify. So it's equivalent to is not in. So hopefully you managed to write a query that selects all the rows that doesn't have M or F for sex in the field, which are all the NAN ones where that data wasn't available. So hopefully you all managed those. If you didn't, you can ask about them in the chat and we'll be happy to help you work out why. So now we're going to look at using masks to identify a specific condition. So a mask can be useful to locate where a particular subset of values exist or don't exist. For example, these NAN or not a number values that we've seen throughout the morning as well. So to understand masks, we also need to understand the Boolean objects in Python. So Boolean values include true or false, which we had a little look at earlier, but we'll just look at them again just now. So if we set x equal to 5, and then I say x is greater than 5, I get a false back, which holds since x is not greater than 5, it's exactly equal to 5. If I then do this, I get a true, which is true. So the double equals is basically saying, is x equal to 5? And we can check. Yes, it is. We get a true. Perfect. All logically consistent. When we ask Python whether x is greater than 5, it says false. It's Python's way of saying no. So to create a Boolean mask, you can you set the true or false criteria, e.g. values greater than 5 should always return a true. Python will then assess each value in the object to determine whether that value meets the criteria and returns a true or not, and returns a false. Python then creates an output object that's the same shape as your original object, so the same shape as your data frame or whatever slice and subset you ended up with. But instead of all of the numbers being there, you would just have a true or a false in every entry. So we'll try it out because I feel like it's always easier to see with an example. We're going to identify all the locations in the survey data that have null. Null means either missing or NaN in place in their data values, and we can use the isNull method to do this. The isNull method will compare each cell with a null value, and if the element has a null value, it will get a true, and if it doesn't have a null value, it will get a false. So we do that by using the Pandas function isNull and passing in our surveys data frame. There we go. So here's like a little piece of it, so we can see that all of the numbers that we used to have all been replaced. So false means that it's not null, which means it is a valid number for that field. And if it's true, then this is probably not a number. So now we can easily find all the places where we don't have valid data for those entries. If we just want to select those rows where there are null values, we can use the mask as an index to subset the data as follows, using the any function. So we get our data frame and we try the isNull of the data frame. And then we're saying any. So that's saying anywhere then you should return a true. Then you should return that row, sorry. So now we've got all of the rows, 4,873 rows, where any one of the columns has a null value present. So the weight column seems to contain a lot of null or NaN values. We can explore ways of dealing with this in the next section on data types and formats. We can also run isNull just on a particular column as well. So we could look for where are all the empty weights. So we'll make a variable called empty weights. And we'll get our data frame. And we want to look in the weight column. Got to make sure to line up all the brackets. And then I'll print out all those empty weights. Here we go. So we can see that there are 3,266 rows where the weights column is empty. We're using the Boolean object of isNull in order to index surveys data frame. And then we're asking it to look only at the weight column. So now we've got one more challenge for this section, and then we'll be having a break. And this one is to look at putting it all together. So it's asking you to create a new data frame that only contains observations with sex values that are not female or male, and print the number of rows in that data frame. And also create one that contains only observations that are of sex male or female and where there's a weight value. And it's also asking you to make a stacked bar plot, like we did in the previous exercise. So you might need to scroll back through your Jupyter notebook to get those commands. So we'll give you about 8 minutes for this one because it's a little longer. Or we can look at this one after the break. So we'll break until 2:15, and then we'll look at the solution to this one. But we'll still be about in the chat and able to go in a breakout room if anybody needs any advice on this one. Okay, hopefully everybody's back from the comfort break and we can quickly go through the answers to this challenge. So it's about making 2 new types of data frames. So in the first bit, it asked us to make a data frame that contains observations with sex values that are not male or female and print the number of rows in that data frame. And then verify it by looking at the other one. So if I put this in here so we can look at the command. So this is selecting from the surveys data frame, and then it uses the isIn function, but with a tilde at the start. So then it's saying anything that is not in, make a copy of it, and then print the length of this new thing. So we get 2,511 rows. And then to verify it, we have a look at whether the sum of the isNulls for the sex column in the original data frame is equal to the length of that new one that we made, where we look for the isNotIn. And it is. So we verified that these are returning the same thing. And then for the second one, we're looking to create a stacked plot again, like we did in this morning's one. So we're trying to select for observations of sex that are male or female, so none of the NaNs, and also where the weight values are greater than 0. So we've got that here. We're looking for sex is in male, female, and weight greater than 0. And then we want the column sex, weight, and plot ID. It's fine. And then we want to get the mean weights. And then we want to create a stacked bar chart like we did before. So if I move this over here. And we can have a look. So yeah, we're grouping by plot ID and sex and getting the mean and using that on stack again to get it out of the data frame and into columns that we can then plot, and we want them as a bar chart. So we've got plot ID against the mean weight, sorry, and the blue is female and orange is for male. So hopefully everybody managed to get that. If you didn't, or if you don't understand the answers, then please feel free to use the chat to ask us for help, or just an explanation around any of this. So the key points from this indexing and slicing and subset section that we've just done is that in Python, the portions of data can be accessed using indices, slices, column headings, and condition-based subsetting, and we've had a go at all of those. Python uses zero-based indexing, so the first element in a list, tuple, or any other data structure always has index 0. And using the Pandas library, that enables us to use common data exploration steps such as data indexing, slicing, and the conditional subsetting. So that's the end of the section that I'm going to be leading, so I'll hand you over to Rui now, who will take you into chapter 4 of the course, and thank you very much for all your work.
Thank you, Laura. There we go. You can see my screen. We're going to start on the data types and formats section. If no one has any further questions to Laura, I'll give you guys a minute to think about that. And before we move to the Jupyter notebook, I would just like to show off a little bit of the interactive Python sessions that you can get in certain terminals, depending exactly on what your system. The most common one would be the python.I, and that should be available anywhere that has Python installed. And you'd get a very simple interactive terminal. The triple caret on the left there means that you're in interactive session, and then you can do things pretty much like you did on Jupyter, x equals 5. And then if you just type x, you get the result, the value of x. You don't even need to use print or anything like that. If you find yourself prototyping a lot on interactive Python, you might want to install the IPython module. It is basically the same TLI, just with a little bit more quality of life things included, like the number of the line on the left, like you have in Jupyter. So it's a bit more similar to Jupyter in that way. There's up and down arrows for things you've run before, even between sessions. And there's a little bit of syntax highlighting that with colors that makes it easier to see if you're making mistakes. For example, if you have a function like print, it will give you the print in green, so you know that's a proper function rather than anything else. But the rest is pretty much very much still the same, with the exception that we get that the 5 is the output from the command number 2. You still get, if it is print, if it's actually the output of a function, you don't get that out number. We can do the first little bit of this lesson in interactive Python. Let me know if you need the font size to be a little bit bigger. I can increase that. We've mentioned, or Laura mentioned in the lessons before, booleans and integers and strings. There are, I don't know, about 10 or so built-in types in Python, from string, integers, floats, complex numbers, lists. Yeah, you can keep your Jupyter running. I'll move back to Jupyter in a second or two. There are objects, which is anything that you create, a class, any class that you create yourself. But then Pandas also introduces some slightly different data types. Some of them that are comparable to the base classes in Python, some of them that are a bit different, like datetimes, for example. So, okay, let's get out of there, and I'll bring Jupyter again. There we go. So I would just I'm starting from a fresh Jupyter notebook. You should be able to continue to use the one you had. If you want to refresh your surveys data frame, you should be able to do this cell here, surveys df, and read the CSV file again, and then you'd have a fresh data frame to continue from now on. So let's have a look at what type the data frame is. So if we do this, we get the output that's pandas.core.frame.dataframe. This is a method of a class of a method of something that is internal to Pandas. Doesn't help us a lot, but we could, for example, it does tell you that it's a data frame, and then you know that any methods or any functions that can be applied to data frames, you can apply to these surveys_df object. Let's have a look at the data types for some of the columns, for example. So if we have a look at the data type, and that's what D type here means, it's data type for, is that enough, Marwa? Or would you like a bit more? Okay, let me know if that's enough. As I was saying, the data type for the sex column of the data frame is data type O. O just means object, which for Pandas it's probably a string. In other libraries it might be something slightly different. If we have, for example, a look at the record ID type, we should see that is int64. Hint here would be integer, the same as the base types in Python, and then the 64 just means that's the 64-bit integers. Here it's the size of how big a number it can contain. And there are other types. These, especially if you're using a lot of NumPy, you might get up to integer 128 bits, for example, if you need really large numbers. If we want all the data types for all of the columns, we could use the dtypes method on the data frame, and then it will just give us a list of all the column headers and what types each of them have. So we have species ID and sex, which are both strings, and they show up as objects here in Pandas. We have record ID, month, day, year, and plot ID as integers, and then we have the height, foot length, and the weight as float 64s. So that's floating point, again with 64 bits of size. So far, we've not mixed different types, but especially numerical types, so integers and floats, you might sometimes want to mix them up or add them together or something like that. By default, if Python needs, it will convert an integer to a float in most situations. But we can have a look, for example, if we print the result of 5 plus 5, it will just give us an integer because it doesn't need to go up. The same would be true for subtraction. But if you divide two numbers together, then the result will be a float and not an integer anymore. These using to be the case in Python 2. So if you come from Python 2, this might sound weird to you, but ever since Python changed to Python 3, this has been the default behavior. If you want, you can convert from floats to integers. For example, if we have a float that's 7.83, and we want to convert that to integer, we can, and Python will just return the integer bit and will drop everything after the decimal point. You can also create a float from integer, and if you do, Python just adds a decimal point with a 0, so there's no loss there. There is loss of data if you go from float to integer, or there can be if the float is not a round integer. Any questions about data types? Okay, let's have a go at changing the data types in our data frame then. Let's say, for example, okay, 2 questions. Does int a change the type of a? Only if you do this. So if you do this, you will change the type of a. Otherwise, the type of a will still be a float as of right now. If I do b equals int of a, then the type of b will be now integer. And if I do a equals the int of a, type of a is now integer, but that's now because I've overwritten the value of a, so a is not the float anymore. Does that answer your question, Celine? So when you call a function on a variable, it doesn't usually change the variable unless you assign that to the variable again. And header, can you specify how many decimal places there are in a float? Yes, from memory, if you do something like 3, it should no, never mind, that's only when you're printing. So when you're printing, yes, there are ways of telling how many decimals to print. I forget out of the top of my head how to do that, but I can get back to you next break and tell you how to do that. But internally, Python, a float will be a float. It's expressed in terms of it's a binary power of 2. So. Okay, so changing the data type of one of our records. So if we have, for example, on our record ID, we can change the type by doing something like this. Using the s-type function, and you can tell it to use float64. Ooh. Yeah, that's because the key doesn't exist. Record ID. There we go. So now, if we remember from here, record ID was an integer. So if we now check the data type, it now tells us that it's a float. So we changed the type of the entire column. So all of the records on that column have been updated now to be a float, a float value. We have a quick exercise. Bring this here. So converting the plot ID to float try that using float rather than float 64, and then try converting the weight column to an integer and see what goes wrong there and what does Pandas tell you. I'll give you guys about 2 minutes to try that one. Okay. Hopefully everybody had some time to try the 2 bits of exercise. Sorry that my screen seems to blank out every once in a while. I think the application is very happy with my connection today. So if we try float ID, this should work as if we used float 64, and indeed it does, as you can see there. However, if we try weight type int, Pandas will complain that we have first, if we spell that correctly, it might help. That's the actual error. Cannot convert non-finite values, being that not a number or infinite to integer. That means that our column weight has some values that are either not a number or infinite, and that Python cannot convert that into an integer type. Only floats can be infinite or not a number. That indeed. I believe that in this case of this data frame is just not a number that happens. And we'll have a look now at how we could sidestep that issue or correct that issue on our data frames. So, for example, if we were to do the mean of the weight column, we get a result that's 42.67 something something. So a float, and this time a NumPy float, 64. Brains Vasco. So I didn't actually assign the new type to the surveys. So only if I had done this would the changes be reflected. So because I didn't assign, I just, again, I used the variable, I didn't change it. That's why if you see here, the output from Jupyter shows a float, but then if you go check again, the original is still an integer. Okay, so the Pandas allows us to calculate the mean even if there are not a number values in a column, but that's because Pandas was created in a way that allows for that. We should still be careful while doing data analysis about those values and handle them appropriately. Depending on the situation, you might want to completely disregard the columns where that happens, or you might want to assign a default value to that or some other variation, for example. Let's have a look at how you could find, for example, how many of those you have. So you could look at the number of not numbers, values that you have on a particular column. And for that, we could use a construction like this. So this creates a Boolean mask like we used on the previous lesson. Selects them this bit creates the Boolean mask and then selects those values from the service data frame. And then the length function gives us a number of rows. And in this case is 3,266 rows. A slightly different construction that we could use would be, just to reuse this a little bit, we'll say where the values in the column are greater than 0, and then using the length function again. Oh, sorry, that's the opposite. That gives us how many have values, not how many RNA. There goes my screen again. Apologies for that. Okay, I think we're back. So if you want, for example, to replace all of the not a number entries on your data frame with a value, for example, 0, you could do so using the fill NA method. Let's save our original values and modify a copy by copying the original data frame into the F1. So now we have a copy of the entire data frame here as the F1. And now we can modify the weight column by doing something like this with the fill NA method. And here, for example, you can fill zeros, but you could use a different value inside the parentheses here. And if we do this, and now we check the mean again of the weight column, we can see that it will be vastly different from the value we had before we changed those not a numbers to zeros. So again, depending on the objective of your data analysis, you'll want to be careful with those not a numbers and handle them appropriately for the precise type of data analysis that you're doing. Another way to handle this, and usually, or at least probably more common, would be, and here I'm going to be replacing what I did here, be to use the mean of the values that already exist. And I'm doing that by passing the value to fill NA, by passing the value of the mean of the data frame that still has all the not a number values, replacing the not a number values in that column with the mean, and then replacing the column on our modified data frame with the result from that. And now if I run these again, we get the original mean that we had before. So we replaced all of the not a number records into the mean of that column. So that way we're not polluting our data in that way. But again, how you do this will depend on precisely what kind of data analysis you're doing. We have another quick exercise. It should only take you a couple of minutes. I'll put it here. Count the number of missing values per column. So this would be quick hint using the for loops that we mentioned earlier. Okay. I can show you one solution, but like most things in programming, there will be pretty much infinite solutions to do anything you want. What we can do is something like this. So we can iterate through the columns in the data frame that we have. Didn't want to run that, just wanted to enter. We can print column and then the length of the number of rows that are not a number. So by using, for example, the isNA function. So we're selecting all of the rows where the column that we're iterating through is not a number, and then we're printing the number of records of that against the name of the column. There we go. So record, month, day, year, and plot all have completely filled records, and then there are 763 missing ones on species ID, 2,511 on sex, 4,111 on hindfoot length, and 3,266 on the weight column. There any questions about that? Anything you didn't understand how to do that, or how I got to this point? Okay. Do write in the chat if that's not the case, but I'll finish this last bit of this lesson before we do another quick break. So the last bit here is out. We've been looking at reading things and modifying things. Now we'll be starting to look at how to write data back to files so that you can come back to later or use elsewhere, being it on for other analysis or for plotting or to send someone. So what we can do is Pandas has the same way that it has a read CSV function, it has a toCSV function to write it out. So I'm just going to refresh the service_df variable that I have so that it's fresh, read, without any of the modifications to types that we've done before and stuff like that. And then I'm going to create a new data frame that is all of the records in the data frame that I just read, except that I'm going to drop all of the lines that have not a number values in it. So if I now check this new data frame, we can see that it only has 30,676 rows, even though the index goes up to 35,000, which is the same as the original data frame. We can, and as you can see here, it starts in 62. I'll wait until it comes back. There we go. It starts in 62 instead of starting at 1. If we want to recreate these index column, what we can do is using index equals false when you write it down. So, for example, if you're writing, sorry, that's I believe that's here. We can use index equals false. We can also, indexes are not used, especially when you're writing to file. So here, it's not going to be relevant. So if you want to write this data file here, before I start writing, if your folders looks anything like me, which is I just have the notebook and the data folder where all the CSVs are in, so the ones that we downloaded from the website, we need to create a folder to write our outputs in. You can do that by importing the OS library and then doing os.make directory, and then I'm going to name mine data.output. And then if we see here, you go back, we can see that there's now a data_output folder. type emitter is now completely empty. And now I can write my data frame to that folder using the to_CSV function from Pandas. And I'm going to write it to that data_output folder. And then I'm going to name it surveys_complete.csv. And I'm going to tell it not to write the index column. So just like the file we had read previously, it doesn't include the index, Pandas creates the index. So we're going to do that. We're going to use these files later in the next lesson after the break. But just to show you that surveys_complete now shows up on my data_output folder, and it was modified 13 seconds ago. So we can go into break now. I'm happy to answer any questions about this entire lesson. Otherwise, I'll see you back at 3:15. Okay. Let's continue the next lesson then, which should be about merging data and merging data frames in different ways using Pandas again. If you're working with actual real data, you'll come across many situations where you'll either have, for example, the data for each year on a different file, or you have different types of information on different files, and you might want to merge all that data into a central data frame that you then want to manipulate. You can use that in Pandas using the merge and the concat methods, and we'll have a look at both of them now. Just to make sure that my data frames are fresh, I'm going to read everything again. You might want to do the same depending on what you've been doing with your data frames. So. And just to make sure, yep, there we go. And now I'm going to read a new data frame, something we've not been looking at yet. And this is the species data frames. And this is a different file that should be on the same zip folder you got. It's named species. And we should see that this one is comprised only of 4 different columns. It's a lot less rows as well. And you see that it has in common with the survey data frame. It has species ID, like this one. The values in both will be common. And then the species data frame has 3 more columns, genus, species, and taxa, that we'll want to merge onto the service data frame that we've been using so far. So how can we go about doing this? Well, depending on what we want to do. So if you want to add more rows or more columns, let's create a few subsets using the techniques we learned on the previous lessons, so that we can work with these on a smaller scale before we go full scale on all of this. So if we have a subset of the survey data frame, surveys TF, so the first 10 rows using the head method, we can then have a look at how that looks. So that's the first 10 records for the surveys data frame. And we should be able to do the same for the last one. Okay, so last 10. And we can do that using the tail command, which is the opposite of the head one. If we have a look at those, you'll see that the record IDs are high, so it's the end of the data frame. If we want to change the indexes here, but it will keep the records, what we could do here is reset index. I don't think we'd need that. And no, we did. So we need to tell it to drop the old index, otherwise it saves it as a different column. Capital T. So now we have the record ID, which is the old values, and we have the new indexes, which are 0 to 9 again. So now with these two smaller subsets, so survey underscore sub and survey underscore sub last 10, which is the first 10 and the last 10 rows, what we can do is have a look at the different times of stacking or concatenation. So we have what's called vertical stacking, which would be using the Pandas concat method. And then we give it both of our data frames. And then axis 0, that would be the vertical axis. And then if we have a look at that, the resulting data frame from that, we see that we have the 20 rows from the first subset, and then from the last subset. And we see again that the indexes have not been reset. We could use the same trick, the reset underscore index method, to change those. If we want to do what is called horizontal stacking, you can assume that what would happen is we'll have more columns rather than more rows. We can use the concat command with, just gonna copy this. It's the same command, but we're starting it over the axis number 1, which is the horizontal axis rather than the vertical one. And if we have a look at the resulting data frame, we'll see that we have repeated columns now. So for our type of data, this would be a wrong way of merging and concatenating things. We're just messing up all the data. But in certain cases, and we'll see next, this might be what you want to use, is to add more columns if you have files that have rows for the same data with different columns and different information. Does that make sense? Or are there any questions about concatenation method? Okay. We can have a go at the challenge next then, which is combine data. So this one. So it says that in the data folder, there's another folder called yearly files. That is not the case for me. It might be if you downloaded the zip. I downloaded the files individually, so I have them all under data only. But there are two files named surveys2001.csv and surveys2002.csv. The exercise here is to read both data into different data frames, and then using Pandas and the commands we've just had a look at to make to combine them into one data frame. And then as an extra, using some of the stuff we learned on previous lessons to create a plot of the average of the weight column after grouping the data by sex. And then finally export the results as a CSV file with the to_CSV method we saw before the break, and then make sure that you can read that CSV file using the read CSV method. This This might take a little bit more than 5 minutes, but in about 5 minutes, I'll ask how everyone's doing, and then we can see from there if you need a little bit more time or not. Okay, let's have a look at how you can solve that exercise. Bring back to the Jupyter notebook. So the first thing we had to do was to read the two files with the yearly data. So survey 2001. The other way around. And survey 2001. And then just quickly do the same for 2002 with a different file. Now we'll want to concatenate both of those files into a new data frame. And like we saw before, we can use that with the concat method. So let's do survey 2001 and survey 2002. And because we want to add rows, we want to use axis equals 0, which is the vertical axis. So now if we print the new data frame, you see there's 3,000 rows and there are no repeated columns here. So the next thing we want to do is to get the average or the mean of the weight column after we group by sex. So we can do that, we can put that into a new variable. And we can group by first using both the year and sex columns. And we then want to select the weight column to do the mean. And then once more, like on the previous lessons, we want the unstack method to convert that to a simple data frame, not a recursive one. We can have a look at this. As you see there, very simple data frame. Finally, to plot this, we can use this data frame, and we can use the bar plot, for example. And we can have here separated by year and by sex with different colors and everything. The final thing would be to write these data to a CSV file. So that's the toCSV method, and I'm going to write that to data output folder and wait CSV. And then if we want to check that that was written correctly, we can try and read that again. There we go, and we see the same data we had above. Are there any questions about the exercise before we move on to the other kind of merging data frames? Seni asks if there's a default axis for concat. I don't know, but it should be easy to check. So if we get this, and I'll just create a new cell down here, and we don't give it anything, it doesn't complain, so it probably is axis 0, and we should be able to check that by printing the information there. So yeah, again, 3,512 rows with no repeated columns. So axis 0 would be the default. Any other questions? Okay, you can also ask at the end. I'll stick around for a bit, but then we'll move now into a slightly different way of joining things. So far we're just adding things to the bottom or to the right willy-nilly, but sometimes if your data in the two data frames is slightly different but related, you might want to extend the data frames in a slightly smarter way. So if you remember, we had a species DF data frame that had the genus, species, and taxa information correlated to each species ID. This will be similar to some of the things we'll do tomorrow using SQL. So this was what's usually called merging tables. Okay, my screen's back. So imagine, for example, that you want to join these two data by extending the original surveys, adding the genus, taxa, and species, I think it is, by correlating with the species ID that exists on both tables. How could we do that? And what would you gain? Well, it'd be easy. So if you only have the species data separately, you need less storage, because on the main records, the one with thousands, tens of thousands of lines, you're only saving a few characters per species ID. And it also allows you to be consistent, so that if you had a typo, for example, on one of the taxa here, you would just have to fix it once, and it would apply to all of the species that have the same species ID. So that's one of the main reasons. I'm sure there are many more that you could think of, but data savings and consistency of data are two of the main ones. So how could we go about doing that? So let's create another subset, just so that when we're having a look at things, we don't have to scroll through thousands of lines. Again, I'm going to take the first 10 surveys, the first 10 lines of the whole surveys data frame. Will be those 10 lines. And then I have the species data frame. No, I meant to create a subset as well. Let me see if I have this file. Oh, we do. Okay, from the species subset file. Okay, so two subsets of both the survey and the species. Let's have a look at what this one has. Also, just 3 species, which would be the ones showing up here. Okay, so now what we need to do is identify how we're going to join the two data frames, and this is usually done by what's called join keys, or what column we're going to use as the identifier that will allow us to join both data frames. So what we can do is have a look at the column names. So on the species subset, we have those 4 column names, so the species ID, genus, species, and taxa. And then on the survey subset columns. We have a few more. This is the one we've been working with all day, but including there, we have the species ID, but none of the other three. So the species ID would be a great join key to use on when we're merging different data frames. How you merge depends also on what kind of data you're after and how you're going to analyze your data. There's a few different kinds. Let me bring down here our course material, which has, I think, one image or two. So this is what's called an inner join. This was with only keep the data that's common to both data frames. So in our case, we can have a look at what that would look like. Second. So if we have a look at the inner merged, we use the merge method here instead of the concatenation, and we tell it on the left we want the survey subset, and then on the right we want the species subset, and we need to tell it how to which is the join key. So this is using the left on and right on keywords. Right on. So then we need to tell it what column we're using. So if the column name were different in the two data frames, you could still use the columns if they had different headers. For example, you just have to keep them the headers here. In our case, they're both named the same, so we should be able to use the same name on both. So now what we can check the shape of these merged data frame, and then we can also have a look at what it looks like. So we have lost a few lines. So we had 10 lines. We seem to be missing 3, 4, record ID 6 and 10. No, should be, yeah, we have 8. So we lost 2 of our records. So that's what the inner join does. It only keeps the records that exist on both subsets or both data frames that you join. So in our case, let's have a look at 6 and 10. They probably had a species that was neither of these 3. So D, M, and L, and P. So as you can see, yeah, 10 was PF, and so was 6. So because PF doesn't show up on our subset species underscore sub data frame, they are discarded when you do an inner join. Another way of doing joins, and there are a few. One that I'll show now is left joins, and in this case, instead of just giving you what's common in both data frames, it gives you everything that exists on the left one as well as the common bit. So it just basically adds the information from the right data frame to the left. So there's a question about how there's only one P. I'd expect at least each species twice. Why would you expect that? So we're just adding these 3 columns here to the left data frame, which would end here beforehand. We're just extending with the new columns from the species data frame. So this is not a concatenation anymore. We're adding information to the data frame we already had. On the case of the inner join, you'll drop the rows that with data that doesn't exist on both. But on the left join that we'll do now, we can have a look, and you'll keep the PFs, but just won't have information on these lines. So if we do, let's have a look at that. So adding the right data frame to the left. So in the inner merge, well, you're always adding the information on both. On the inner merge, you're dropping any rows that don't exist on both. You're dropping rows where the column that you're using as a join key doesn't exist on both. On the left merge, which is what we're going to do now, you'll keep all the rows on the left data frame and just add information on the right to the rows that that it makes sense to, that where there are keys in common. And then you can also do a outer join where it'll just add the records of both. But PE only exists in one. No, I believe PE exists in both. Yeah, it exists in this one, and it also exists in this one. PF is the one that only exists in the species one. So it's line, record ID 6 and 10, which was the ones that we dropped on the inner join down here. So you can see there's no PF, there's no record 6 and record 10. Does that make sense, Lorenzo? We only have one PE on the file merge because our left data frame only has one PE, which is record ID 7. So then we're just adding the information to the right, 3 new columns to the right of this with the genus, species, and taxa. That's okay. If you want to stay, once we finish the session, we can have a chat. Sometimes it helps to talk about it. Right, going back to left merge, pd.merge, and pretty much the same. So let me just copy this. The thing that we'll want to add is the how keyword. So by default, Pandas does a left inner merge, sorry, but now we want to do a left merge. So we add the how keyword to the method. And if we now print the merged left, we now see that we kept all the 10 records. But on the case of the PFs, where the species sub data frame doesn't have any information, we just get nans. We just get not a number, not a value, nulls, basically. That's okay, Lorenzo. Data frame merges are not the easiest things to get. So just to finalize, there are a few other types of merge. Right merge is pretty much the same as left, but you are focusing on the data frame on the right. This would be basically the same as a left merge, where you swap the order of the data frames. And then a full outer join, a full or outer join would be you keep the records from all of both data frames, depending, regardless of whether they exist on the other one or not. It doesn't usually make sense, full outer joins, but there are a few specific circumstances that they might. Self join, something that's also not very common, but it's where if you want to compare records within the same data set, for example. I believe this is an article on DevGenius, yeah, where you can have a read of a lot of them. We are nearing the end of today's session, but we do have a couple of challenge exercises if you want to have a go at it, and I would recommend you do. If you are tired and want to head off, we will restart tomorrow at 9:30. But me and Nathan will be around today until 4:30 or so. if you have any questions, if you want to have a go at this, and I'll, in about 10 minutes or so, I'll show you the solution for both of these. But if you really need to go, the actual teaching part is done for today. Right. Anyone have any question about these two exercises that you'd like explained? I did quite quickly paste all the commands needed for both on my screen. No. If there are no questions, I'll stay around a little while, but thanks everyone for coming. I'll now finish the recording.